Okay, so center of mass of a continuous system by integration. Let's start with the example of the position of center of mass of a solid hemisphere of uniform density. So you can see that the diameter of the original sphere, which is bisected to form the hemisphere, would be the symmetry axis. So the center of mass would lie somewhere on that. Okay. So just try to figure out how we would take the differential element accordingly. Right. So we have a couple of options about how we can slice this hemisphere. One option is we can slice it into discs. Okay. The other option is that we can slice it into shells. That's also there. Okay. Since you already know the formula for center of mass of a thin hemispherical shell, so we can make use of either of these. Okay. So I will go with the method of discs first. So first of all, if this is our original sphere, which we have sliced out into half. So this is a solid hemisphere now. So once again, I'm taking the y-axis as the axis of symmetry. So the base of the hemisphere is lying in the xy plane, sorry, the xz plane, with the center of mass, the center of curvature being the origin. So now what we will do is we will slice this into discs like this. Okay, as if we have cut it or sliced it using a plane which is parallel to the base of the xz plane. So that kind of situation. Okay, so if we take this as a differential disk, So what we'll have to do here is we'll have to understand that while the solid hemisphere has mass m and radius r, but when we consider the thin disk, okay, we'll have to consider its radius as this one, small r over here like this. Okay, this is capital R. This position is y, and we'll have to take the thickness of the disk this time as not the thickness on the curved side, but the vertical thickness. Okay, so this is where there's a difference between a disk, a solid disk like we are seeing over here, and a ring which we had seen in the case of the area on the surface. Okay, so we are not concerned with this thickness. No, we are concerned with this vertical thickness, this thickness of the disk, this one, which is dy. We will take the differential disk of radius small r and thickness dy. So it has a volume of pi r square dy. Now you can see from the trigonometry of the triangle that r square is equal to capital R square minus y square. Next thing we can understand is that the mass of that disk, which is density into volume, become m upon 2 by 3 pi r cube into pi r square dy. We can write like this. This is that mass of that disk. Okay. So now when we want to understand that y-axis being the axis of symmetry, the center of mass is at some position where the y coordinate is integration y dm divided by total mass. Dm here is rho dv, and this rho dv is like this. So now we need to substitute in the integration. And aside from this, we can also see that we can use this to prove that volume of a hemisphere is 2 by 3 pi r cube. So anyway, now we'll substitute here. So this is the integration we have to come up with now. So just complete this, we will. Okay, so anybody got the answer for this?
तो कोई नई दवाई मार्केट में आती है
Yes, that's correct, Manav. So let's complete this integration here. M cancels out and this integration gives us r square y square by 2 minus y to the power 4 by 4 going from 0 to r. That will give us 1 by 4 into r to the power 4. Half minus 1 by 4 will give us 1 by 4. So from this we'll get the y coordinate of the center of mass as 3r by 8. Whereas in the case of hollow hemispherical shell, you remember it was r by 2. Okay, people. So with this example, we complete our discussion about the position of center of mass for the standard types of applications of integration, including semi-ring, semi-disc, hollow spherical or hollow hemispherical shell, solid hemisphere, solid cone, which we saw last time, and also the general formula of an arc subtending an angle alpha, the position of the center of mass. Okay, so this is the point where we move on from this section of this chapter, system of particles, that is from the section of center of mass calculation to the next section, which is the application of conservation of linear momentum for collisions. Okay, so our next, it's almost like a new chapter actually, but it's within the same section. So collisions is the next part of system of particles that we'll study. So a collision is nothing but an impact between multiple, that is two or more moving bodies, okay, such that there is some transfer of momentum from one to the other because of some kind of mutual impact forces. Okay, so a collision is an event involving an impact between two or more moving bodies, okay, and transfer of momentum among the colliding bodies due to impact forces. For example, if we have a situation like this, on a smooth horizontal surface, let's say we have two blocks that are moving in such a way that they're moving along the same line, and they're moving along a path that eventually they're going to come in contact. So we have two blocks like this, which are moving with some velocities, UA and UB, let's say, towards each other. So A and B move uniformly along the same straight axis, the same axis at the velocities UA and UB, and collide such that the impact forces or impulse are also along this same axis. So this is an example of what we call a head-on collision. This becomes an example of a particular type of collision called a head-on collision between two bodies. So what will happen here is that as they come in contact somewhere in between, they will be applying force or impulse, that is force acting over a certain amount of time creates an impulse. So this is, let's say, the impulse that A will apply on B, and this is an equal and opposite impulse that B will apply on A. Okay. So this is the collision impulse. Remember, impulse is equal to force integrated over time. So this is the collision impulse applied by the body A. on B. And similarly, this is the collision impulse by B on A. So as a result of this impulse, there is exchange of momentum between them in such a way that eventually what we might observe is that after they have lost contact again, now they might have reversed their direction of motion, or at least in case of A, instead of reversing, it might have slowed down, but moving in the same direction. Both the possibilities are there. Suppose we are assuming that it's reversed. The final velocity of A has become in this direction, the final velocity of B has become. So this is an example of a head-on collision, where what is happening in the head-on collision is that the final velocities, that is the velocities after impact, VA and VB, are along the same axis as the initial velocities. Okay. Hence, it is the head-on collision is also called a one-dimensional collision. Okay. So this is just one example of a collision event. Okay, there are many other different types of collisions that can occur, but in general, any event where two or more bodies, moving bodies, are colliding with each other or making an impact on each other, such that they transfer momentum among themselves due to collision forces or impulse that acts. Such type of an event is called a collision, and we will learn very soon that in all collisions, the total momentum of the system, that is the linear momenta of all the colliding bodies added up, that is the total momentum of the system, is always conserved, because during the event of the collision, there is no external force. Whatever force or impulse is acting is within the system in action-reaction pair. So the net external impulse is zero. So momentum of the system is conserved.
Sir, impulse is like momentum, na?
Sorry, come again. Can you speak a little
Sir,
louder, please?
impulse will have the same units as momentum, na?
Yes, impulse, the net impulse on a body is equal to change in momentum. So impulse and momentum have same unit. Okay, Tejas, I'm going through the question that you've asked. Change in momentum must be very high compared to the time. See, the thing is, Tejas, you cannot compare things like time and momentum, no, because they're of different units. But yeah, the change in momentum is comparable to the amount of impulse. So if the net impulse has a certain amount in Newton seconds, that is exactly equal to the change in momentum in kilogram meter per second, because Newton second is the same thing as kilogram meter per second. So for example, if a force like you have shown over here of, I don't know, 10 raised power 8 or whatever Newtons is acting for 5 seconds, then it's going to create a very large amount of change in momentum. But on the other hand, if such a large force is acting for only a microsecond or a nanosecond, then it will not cause such a large change in momentum. So when two bodies collide, actually the time of contact is very short, even though the collision force is of very large magnitude. That is why the change in momentum is not a huge amount. Okay, it does not set the bodies into motion with a very, very high velocity like that. Okay, because even though the force is very large, the time of contact is very short. So the time for which the collision is happening or the forces is acting is not going to be in seconds or even milliseconds. It's probably going to be in microsecond range. Okay. No, the whole question, Tejas, is the in defining the impulse. Okay, if you are calculating impulse from the definition of impulse, that it is force integrated over time, you have to actually consider how much time that force is acting for and what is the magnitude of that force. So for example, if it is a constant force acting for a time delta t, then the impulse is just F into delta t, where F is the constant force, delta t is the amount of time for which it is acting. So for example, a 50 kg block in free fall for 1 second, the impulse due to the gravitational force will be its weight into 1 second. Okay, so it will just be 500 newtons into 1 second. So that will be 500 Newton seconds. So it will create a change in momentum which is of that much. But if the same body was in free fall for 10 seconds, it would create 10 times the amount of impulse. But like that, when we consider events like collisions, okay, the impulse is of slightly different nature because it's not a force which is continuously acting over a few seconds or over a large duration of time. Rather, it is a very, very high intensity force. That means that magnitude is going to be very large, but it's acting for a very short duration of time, probably in microseconds. And also the force is not going to be constant like gravitational force. As the bodies come in contact, the force will increase from 0 to some peak value and then again dip to 0 as they lose contact. So we cannot really understand that without doing some kind of detailed experimental analysis. But by just looking at the momenta of the body before and after, we can calculate how much the impulse is. That is why in case of collisions, we talk more about impulse rather than force. No, that is the point. Okay, the time duration that we take is according to how much time the force is acting for. It's really about that. The impulse is determined by two things: the force and the time. So if the force is acting over a long duration of time, it might be acting over 1 hour. Then we'll have to consider the impulse as force integrated over 1 hour.
So,
Yeah.
so the time will be the contact one, like till
In
how
case of
much time they
collision
are in
impulse,
contact.
yes. In case of collision impulse, it will be about how much it'll see. The time is about how much time the force acts for. So in case of a collision, the mutual force acts only for that much time as they are in contact.
Okay.
And typically that contact time is very short. In an average collision between two bodies, like the example I've given you over here, it's not going to be a long duration of time. Okay, let's look at another example of a collision. Now, this is something that you could probably observe in a game of pool or even carom. Suppose this is the top view of your carom board, and this is the striker, and somewhere else you have a coin over here. And now you aim the striker at the coin in such a way that you don't aim it dead center, but you aim it slightly off center. Okay. Then what happens? So if the coin is at rest initially, but the striker is aimed with a velocity u like this, Now that velocity vector is not passing through the center. So what will happen is that when they come in contact, the situation will look like this. This is the striker, let's say, okay, and this is the coin. Okay. So as they come in contact, okay, because they are round objects, discs kind of thing. So the line of action for the force that they apply on each other will be like this. It will be along the center to center line, because they come in contact such that the plane of contact is the tangent plane. So it's like a normal contact force which has to act perpendicular to this tangent plane. So the direction of the collision force and therefore the collision impulse that will act will be like this. This will be the impulse on this. This will be the equal and opposite impulse on this. Okay. So as a result of that, what will happen is now this body and this body will have different directions of motion. So notice that this one was initially coming along this direction. So its initial velocity was, let's say, along this axis. So it was along this kind of an axis, the initial velocity. So now this one's final velocity will become something like this. And this one's final velocity will be in this sort of direction. So because now the initial and final momenta are not along the same axis. So it's not a one-dimensional collision. It is a two-dimensional collision, or what we call an oblique collision. Okay. So here this is called an oblique collision. So the final velocities, that is v1 vector and v2 vector, are what we call non-collinear. So it is an example of a two-dimensional collision, or a what we call an oblique collision. So impulse applied by A on B will always be equal and opposite to impulse applied on B on A, by B on A. So it will be minus of this. This is coming from the concept of action reaction. And hence, momentum will be conserved for the system. Now that same thing applies here also. If this is A and B, this is the impulse that A experiences because of B. This is the equal and opposite impulse that B experiences because of A. And as a result of that, the same thing will apply here also. A plus B as a system will have conserved linear momentum. So we will have mass of A into whatever that initial velocity of A was. That will be equal to mass of A into final velocity V1 plus mass of B into final velocity V2. Whereas for the above example, when we write the conservation of linear momentum, we get a much simpler equation. We'll get the equation here that minus MA UA plus MB UB. That will become, sorry, this is plus, this is okay. Let me write this better. So conservation of linear momentum for this above example for the first example, this will give us example 1, this example 2. So this will give us that MA into UA minus MB into UB is equal to minus MA into VA in my diagram plus MB into VB. So that will be the conservation of linear momentum equation for the first example, which was a one-dimensional example with the directions like this. Whereas for the second example that I've taken, because it's an oblique collision, so we have to write it in vector form. We cannot write it as a scalar form equation with algebraic signs. This one you can see it's a vector relation. So later when we are solving those kind of things, we'll have to solve them by using vector algebra. Whereas the head-on collision, we don't have to use vector algebra because it's a case of collinear or one-dimensional vectors. So we can just use the scalar notation. But the important thing is in all collisions, momentum is conserved. Whether it is oblique or one-dimensional, that is head-on, okay. Whether it is just two bodies colliding or more than two bodies colliding, okay. Momentum conservation is applied in all collisions. Principle of linear momentum conservation applies to all collisions. So as we go along, we'll discuss about more types of collisions and the various techniques applied and the classification of collisions into different categories, etc. So today we will start with the simplest of the collisions.
So,
Yes.
so in second example, could you explain again how the final velocities become non-collinear?
Because see what is happening now, B पे जो impulse लग रहा है, that is along which direction? It is not along U's direction. No? You can see in the vector diagram, U was not along the center to center line. No?
Yes.
So B was at rest initially, and then an impulse is acting along some different axis, no? Not along the axis of U. So what will be the direction of V2, B's final velocity? It will not be same as U.
Yes.
Okay, now similarly, what will happen? A पे जो impulse लग रहा है, the one that is acting in the upward sort of direction. In the sort of, you can say, if you go by that kind of situation, you can think of it like a northeast kind of direction. So that is not along the same line as the initial velocity vector was. That I've shown in the middle diagram as the green dotted line, the initial velocity. Whereas the impulse you can see is along some different line. No?
Yes, sir.
So that is why its momentum will not be in the same direction. No? It will be. Got it now? Understood?
Yes, sir.
So that is why you know that in carom, if you aim the coin or if you aim the striker dead center of the coin, then it will hit in such a way that it goes along a straight line. But if you aim it off center, like I've shown in the first diagram, for example 2, then it does not go in the same direction. They go off at some angle after hitting. No?
Yes, sir.
So that's the reason that why it happens, because you're aiming it obliquely such that the collision forces or the collision impulse is not acting along the line of the initial velocity. That is why there is an oblique situation that occurs.
Okay, sir.
Right. And of
So,
course, we will learn to do all the calculations based on this and all also. Okay. So this is just to get you familiar with, there are, for example, in case of two bodies colliding, depending on the directions of the motion, we can have two categories. One is the head-on or one-dimensional category, and the other is the oblique category. So what is the definition of head-on collision between two bodies? It is such that final velocities and initial velocities, they should be along the same axis. Whereas what is the definition of oblique collision? They are not along the same axis. Okay, it's a two-dimensional situation. The vectors are distributed in a two-dimensional plane. They are not along the common axis.
Sir, so impulse will be from center to center, na?
Yes, in the case of,
And
see, this is like, we are assuming it's like two discs, no? Like on a carom board. So when they come in contact, what type of force acts? It's a normal type of force, normal reaction type of force. So because of the geometrical condition, no? When two cylinders come in contact, what is the plane of contact? It is the common tangent plane. So the force that will act will be perpendicular to the tangent plane. No? It will be a normal force. So it will be along the center to center line.
yes, sir.
Okay, understood why it's along the center to center line?
Yes, sir.
Okay. Okay. Now, for example, we can also have another situation where something like this is happening. We have, let's say, two objects, like two spheres, which are kept quite close to each other, maybe even in contact. But in this case, I'm not drawing them in contact. I'm just showing them very close to each other, kept like this. And now we have a third identical sphere, which is initially somewhere else. Okay. But it's moving like this, and it's going to hit these together. Okay, so it's like, let's say it's going like this along this line, and after some time it comes in contact with both of these together. So there is some impulse that acts on this, there is some equal and opposite, there's some impulse that acts on this, and these two together are applying some net impulse on this, let's say like this. So as a result of these impulses, okay, what we observe is that these two bodies go off with some velocities like this, let's say, and this one maybe recoils with some velocity like this. But even in this case, what will happen is that the vector sum of these impulses will be zero. Okay, so net external impulse on the system of A plus B plus C will be zero. So therefore, linear momentum will be conserved for the system. So our mass of A into U, which is the initial momentum, because both of these I'm assuming were at rest, that will be equal to the final momentum, which is the vector sum of these three individual momenta. So this is an example where a moving body A collides simultaneously. Okay, and also you can see obliquely. You can see in the diagram that it's an oblique collision with two bodies, or you can say two stationary bodies. So these are all everyday type of examples which are easy to visualize of collision events. And you can see in all these different categories of collisions, one common physical concept is that the linear momentum of the system is conserved, because the collision event only involves the application of mutual forces between the colliding bodies. So whatever force A applies on B, B will apply equal and opposite on E. Whatever force A applies on C, C will apply equal and opposite on E. So the external impulse on the system will be zero. So the linear momentum of the system consisting of colliding bodies, whether that is two bodies colliding, three bodies colliding, whatever be the case, the whole system's linear momentum before and after the collision is the same. It remains conserved. Okay, so this is the first and most important aspect to understand about any collision, that linear momentum of the system will be conserved.
Sir,
Okay, so now next what we'll do is we'll systematically understand how to apply equations and solve situations.
So,
Yeah.
so in the example, this example, you told next external impulse is 0. So in the previous examples also, every time next net external impulse will be 0, right?
Yes, that's why the linear momentum is conserved. No? We had written that equation that the impulse acting on A because of B is minus of the impulse acting on B because of A. That's why the net external impulse is 0, right? They cancel off an
Yes.
action reaction pair.
Yes.
Okay, so we will now go step by step in understanding each type of collision. So first category of collisions we will see is head-on collisions. Head-on, or they're also called one-dimensional or 1D collisions. So in this, what happens is that by definition, the initial and final velocities are along the same axis. So the initial and final velocities of colliding bodies or particles are collinear. That means they are along the same axis. Okay, so if we look at the general situation like this, that a particle of mass m1 moving at a velocity u1 along this axis is colliding with another particle of mass m2, which is also moving along the same axis. They could be moving in the same or opposite direction, but importantly, their vectors, velocity vectors, are collinear. So this is the situation before impact. Now, as they come in contact after some time, what will happen is they will apply equal and opposite impulse on each other. Okay. And that impulse will also be along the same axis. So therefore, after impact, the final velocities will also be along the same axis. So here I'm just assuming that V1 has not become reversed. It has just reduced in magnitude compared to U1 because of the impulse. So with the sign convention that I'm using over here, we will see that conservation of linear momentum for M1 plus M2 as a system will result in the scalar equation that M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Okay. And if we consider the collision impulse, okay, by using the impulse momentum theorem, that net impulse acting on any body or particle is equal to the change in its momentum. Okay. So using that, the collision impulse can be calculated like this, that on M1, the impulse acting is minus J, and that is equal to the final velocity, final momentum minus initial momentum. Or on M2, the impulse will be acting in the positive direction, and that is M2 V2 minus M2 U2. But more important for us is this equation. This equation comes from the conservation of linear momentum. Okay. So for example, if we have a situation like this, okay, where a block of, let's say, 2 kilograms collides with another block of, let's say, 1 kilogram, and this one is at rest, let's say. Okay. So M1 at a speed of 12 centimeters per second makes a head-on collision with M2, which is at rest. Now suppose after impact, M2 starts moving at, let's say, just a minute. At 16 centimeters per second. Okay, then find m1's final velocity. Okay, and the collision impulse. Both these things we have to find. Okay. So if you observe in this, a lot of information is given to us. Not only the two masses, but the two initial velocities and one final velocity is also given to us. The final velocity of the second object is given to us. So there's only one unknown quantity, which is the final velocity of the first object. So we just need one single equation to find that final velocity, and that will come from what? The momentum conservation. So use momentum conservation to find V1. V2 is already given to us as 16 centimeters per second. And once you found V1, okay, the next thing you can calculate the impulse by using the concept of impulse momentum applied to either the block M1 or the block M2. So very straightforward question. Just try this out, people. Okay, so let's check out the answer, people. Yes, very good. 4 centimeters per second is the correct answer, and the impulse will therefore become, how much it will become? 16 kg centimeter per second, or you can write it as 0.16 kg meter per second in SI unit. It's the same thing as Newton second. Okay, so let's see. So if we see that after impact, the velocities are becoming v1 and v2 for m1 and m2. Just have the single equation that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now this is given to us as 16 centimeters per second. Okay, and this is given to us as 12 centimeters per second, whereas u2 is 0. Okay, so all this information is given to us. So 2 into 12 plus 1 into 0 is equal to 2 into v1 plus 1 kg multiplied by 16. So from this we can see that our v1 is 24 minus 16 by 2, or our v1 is 4 centimeters per second. Now since v1 is coming as a positive quantity, so we can be sure in this case that the velocity is in the same direction. Okay, so this is v1 is positive, so same direction as initial u1. Okay, so that's that. Okay, now as far as the impulse is concerned, on m2 the impulse will be plus j, and that is m2 v2 minus m2 u2. So that is 1 kg into 16 centimeters per second minus 0. So 0.16 Newton second. Now you can just verify that is the same, because you got the answer here. Okay, we can just verify for m1 minus j is equal to m1 v1 minus m1 u1. So minus j should be equal to 2 kgs into 4 minus of 2 kgs into 12. So you can see that it is in kg centimeters per second. So this will give us the same result, which kind of justifies that we have not made any mistake in solving. Okay, now the next aspect we'll understand is that depending on the type of material with which the particles or the bodies are made, which are colliding, there may or may not be dissipation of kinetic energy. Like, when two tennis balls collide or two soft rubber balls collide, because they are made of highly elastic material, there is hardly any loss of kinetic energy. Whereas if you take two concrete blocks or two wooden objects making a loud impact with each other at high velocity, there's likely to be heating, there might be some denting or some damage created or some change of shape for the bodies colliding, which means that kinetic energy is dissipated into other forms of energy, which are dissipated as heat or sound, or even in the case where the shape of the objects is changing. So energy is utilized into rearranging the intermolecular bonds because the shape of the colliding objects is changing. So in those kind of situations, there is a certain amount of loss of kinetic energy. So based on that, we further classify head-on collisions into these categories. You might have heard of these terms, something called a perfectly elastic collision. So perfectly elastic collision is one where there is zero loss of kinetic energy. Of the system. Okay. Then the second category we look at is something called an general inelastic collision. These are ones where there is dissipation of kinetic energy that occurs. So the final kinetic energy of the system after impact is invariably less than the initial kinetic energy before impact. Okay. And then there is another classification based on this called a perfectly inelastic collision. So this is a type of collision where what happens is that the particles colliding stick together. And move as one single particle. Single isolated body. Okay. So this type of collision also involves maximum possible loss of kinetic energy. So that is why it is also called the perfectly inelastic collision, because the objects are sticking together. So this is just a matter of naming them or classifying them. So we will look at each one in detail now. So let's start with the perfectly elastic collision. But we are still in the category of head-on or one-dimensional collisions. So how we solve this now is that we have the normal momentum conservation principle, but along with that we have an additional equation to write, which comes from the fact that kinetic energy is conserved for such a collision. So once again, if we take the same sign convention for their motion, and after impact, now this is moving with V1 and this is moving with V2. So we have the familiar equation that we've written before, M1U1 plus M2U2 is equal to M1V1 plus M2V2. This is our first equation. This is coming from conservation of linear momentum. This is applicable to any 1D collision, 1D or head-on collision. Conservation of momentum applies to all collisions. In case of any head-on collision, it will be a scalar equation like this. But in addition to this, now we also have this equation that the kinetic energy of particle 1 plus particle 2 before impact is equal to the kinetic energy of 1 plus 2 after impact. So this second equation is coming from the fact that there is zero loss of kinetic energy for the specific situation, which is a perfectly elastic collision. So this is not general for all head-on collisions. It is specific for perfectly elastic collisions. So now what we'll do is, assuming that M1, M2, U1 and U2, these are all known quantities. Okay, so these are known. We will solve equation 1 and 2 for V1 and V2. as unknown quantities, and we'll develop like a general formula. Okay, so just note down the different classifications and up to this step, that is the two equations that we have written, which are coming from the two conservation principles, conservation of linear momentum, and in this case conservation of kinetic energy, because the collision is defined as a perfectly elastic collision. Then we will discuss about how to solve these, because the solving is a little bit tricky. As you can see, it is not a system of two linear equations which are simultaneous. Okay, it involves a second equation which is quadratic in V1 and V2. So we have to apply a little bit of a trick to solve it. Okay, so we'll discuss that. Just write down up to this step first.
Sir,
Okay, so let us look at solving these two equations now. Okay, so as I told that we'll use a bit of a trick to solve these. So equation 1, we will modify it slightly in this way by keeping the terms of m1 on one side. So it becomes m1 into u1 minus v1, and keep the terms of m2 on the other side. So it becomes v2 minus u2. And similarly, equation 2, you modify it by keeping the terms of m1 on one side. Half will obviously cancel out universally. Okay. And keep the terms of m2 on the other side. So we get this. Okay. And now if I divide this, if I do equation 2 divided by equation 1, you can see that you get an additional equation which is very easy to handle. U1 plus V1 is equal to V2 plus U2. Or we get this kind of an equation. Now this additional equation that I've written, it has a huge significance. And the significance of this equation, you can understand from the diagram above. Okay. Before impact, M1 was traveling towards M2 and M2 was traveling away from M1 like this along the same straight line at U1 and U2. So they have what is called an approach velocity. Approach velocity is the velocity at which they are approaching each other before impact. That approach velocity has a magnitude of U1 minus U2. And like that, you can see that after impact, what is happening is M2 is running away at a faster velocity V2. And we have assumed that M1 has slowed down to V1. So they have a separation velocity. They are separating from each other. After impact. And that separation velocity is having a magnitude of V2 minus V1. Okay. So you can understand here that this implies that the approach velocity equals to the separation velocity. So this is an additional property of a perfectly elastic collision. Property of a perfectly elastic collision. And we can think of this as an equation 3 now. So now what we can do is to find V1 and V2, we can solve equation 1 and 3. Okay. So further, solve equation 1 and 3 for finding the value of V1 and V2. Okay. But on the way to that solving of equation 1 and 2, we saw that we have also observed an important property of the elastic collision, the perfectly elastic collision, that the separation velocity of the colliding particles after impact, that is the rate at which they are separating from each other, the distance between them is increasing at that rate. That is exactly equal to the approach velocity before impact.
Sir, if M2 is at rest, then the approach velocity will be the initial velocity of M1, right?
Okay, so given some numerical problem, what we can always do is, if the collision is perfectly elastic, we can generate equation 1, which is the momentum conservation equation. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. This is our equation 1. And instead of the kinetic energy conservation, we can directly write the second equation as actually our approach velocity is equal to separation velocity equation. We can directly write the third equation, which is the fact that approach equals to separation in a perfectly elastic collision. And then this is quite easy to solve, because it's just simultaneous equation. So if we solve these two, we can also generate general formulae. So solving these now, you can observe that. So it's up to you. You can memorize these direct formulae, or you can always leave it up to this step where you solve these equations when you're solving any particular numerical problem. But the formulae are also easy to remember. Solving these, we will get two such terms. And you can see that the terms are quite symmetrical. Both V1 and V2 involve some coefficient into U1 plus some coefficient into U2. And these four coefficients have the same denominator everywhere, M1 plus M2. And the numerators are symmetrical for the diagonal terms. For these two diagonals, or these two terms, it is M1 minus M2 and M2 minus M1. And for the other two, it is 2M2 and 2M1. So it's quite easy to remember these formulae. So you can treat these like the general formulae for perfectly elastic head-on collisions. So this is quite an important set of problems that you will be dealing with in this chapter. The specific case of perfectly elastic head-on collisions. So it's worthwhile actually just remembering the direct formula and knowing how to use them. Okay, so let us look at the application of this with some examples, some numerical examples. So to start with something very simple, let's take a situation where,
Sir,
yes,
can you scroll up for a second?
yes, just a moment. So let's start with that situation where the second body is at rest. This is at rest initially, and this one is coming with some velocity V0, and they make a perfectly elastic head-on impact. Okay. So now, given that M1 is equal to 2 kilograms and V0 is equal to, let's say, 20 centimeters per second, find the final velocities V1 and V2 if we take M2 equal to M1, that is 2 kgs, very simple case, or we take M2 as double of M1 or 4 kgs, or third case we take M2 as half of M1 or is lighter basically of 1 kg. So each of these will get a different set of answers. Okay, so I'll just scroll up from a moment. You can note down what you missed and then we'll come back to this.
So,
This part, yeah, this part or
so
yes,
in the question, V0 is the initial velocity, right?
yes, before impact. So the diagram that I've shown you is before impact. Okay, so the block M1 is coming at the speed V0 and hitting another block M2 which is at rest and is making a elastic head-on collision, perfectly elastic head-on collision. So now for different possible values of M2, in one case M2's value is 2 kg, in one case it is 4 kg, in one case it is 1 kg. So in each of these different cases, we have to find out what will be the final velocities V1 and V2 after impact.
Okay, sir.
Okay, so I'll come back to the question now. So you can either go with the the solving method, which I have shown over here, that you can generate equation 1 and 3, momentum conservation and the fact that approach velocity equals to separation velocity in the case of perfectly elastic collision, and then solve them numerically. Or you can just apply the formula directly and substitute the values of M1, M2, U1, U2 and calculate V1 and V2 for each of the cases. So the full data of the question is below here. Yeah. So as I'm saying that you can either go with this method where you apply these equations and then solve them, these two equations. Okay. There's no need to write the conservation of kinetic energy equation because this equation 3 is coming from that only. So we have incorporated that by using the fact that separation velocity becomes approach velocity whenever the collision is perfectly elastic. So kinetic energy is conserved. Or you can alternately, instead of solving the equations, if you can memorize these formulae, and just directly substitute the values in these formulae, values of M1, M2, all these things. Okay. So work out all three parts quickly. In each part, you'll get a different set of values of V1 and V2, the velocities after impact. So this is the situation after impact. The A part, you should be getting V1 as 0 and V2 as V0 or 20 centimeters per second. So M1 stops and M2 picks up its initial momentum. Okay. So that's something that you can see from the above formulae. So for M1 equal to M2 and perfectly elastic collision, V1 becomes U2 and V2 becomes U1. So that is, they exchange their velocities. That you can see from these formulae above. If you put M1 equal to M2, these two terms become 0 and these other two diagonal terms become 1. So in this particular case, your U1 is V0 and your U2 is 0. That is why the first object comes to rest. They exchange velocities. So in this case, the first one stops and the second one starts moving at the original velocity of 20 centimeters per second. Okay. But that is only for this case when M1 is equal to M2. Now, when you substitute the B and C part, you'll see you'll get different answers. Okay, so let's check out the values. Yes, very good. That's correct, Adinath. So you'll see interestingly in the second case, where the M2 is the heavier object. Okay, M2 is equal to twice of M1 or 4 kg. When you substitute for V1, you will get 2 minus 4 upon 2 plus 4 into 20 plus 0. So that will give you minus 20 by 3. Or you will get V1 as minus 6.67 centimeters per second. So the negative sign shows you that M1 will actually, after impact, it will be recoiling. It will be coming backwards. Whereas M2 after impact will be going in the forward direction, and that you will see is 2m1 upon m1 plus m2. So that's, so V2 will come out with a positive sign. And you can see that the separation velocity will be equal to the approach velocity. As in the third case, M1 is actually twice of M2. So V1 will be 2 minus 1 upon 2 plus 1. So V1 will be plus 20 by 3. And V2 will be 2m1 upon m1 plus m2. So 4 by 3 times 20. So 80 by 3. So this will be the case. So in this case, after impact, M1 continues in the same direction, but with a reduced speed of 6.67. And M2 is running away at a faster speed. Okay. And once again, the separation velocity is equal to the approach velocity. Okay, so whether you go by this formula based kind of method or you write the momentum conservation equations and this thing, if you go by the equations, you can see that you will have m1 v0 plus 0 is equal to m1 v1 plus m2 v2. That's our first equation. And approach velocity is equal to separation velocity. This is our second equation. So you can also solve these. Okay, or you can go with the formula based approach, which I have done. These formula. So whichever approach you go with. Okay. So with this, we conclude today's session, people. Now, a lot of questions in HC Burma, which have to do with linear momentum conservation and collisions, and also position of center of mass. So you can complete up to about question 32 of HC Burma now. System of particles chapter, question 1 to 32. You can try and complete this before the next week. And we'll discuss some of those questions also in the next lecture, along with more types of collisions, including inelastic collisions, perfectly inelastic collisions, and then moving on to oblique collisions once we complete the head-on collisions. So that's it for today's session, people. Wish you all the best.
Bye, sir.
Sir, bye,
Thank you, sir.
Thank you, sir. Bye, sir.
Bye, people, and wish you all a happy Makar Sankranti.
Happy Makar Sankranti, sir.
Same to you.
Yes.
Same do. Sir, can you send the note?
Yes, I will send the notes.
Sir,